In this video, we'll actually be applying the alternating series test to the series we had in the previous video. So this series actually has a very special name because of the way that it appears. I'm going to go ahead and tear it apart so it appears in the form that we should be utilizing in the alternating series. That means I'm going to pull the -1 to the power away from the actual series term, and the series term I have is 1 over k. You'll recall that the term 1 over k is actually the harmonic series, so this series actually has a special name of the alternating harmonic series. And we can basically make a conclusion about whether or not this thing converges with that statement later on. So we're going to go ahead and use the alternating series test to see whether or not the alternating harmonic series will converge or diverge, and then we'll be able to make this statement every single time we see the series. Heck, we could probably even use this series with, say, the comparison test or limit comparison test where necessary, although, again, those two tests both require that all the terms be positive. So we won't be using this in that case, but we can use it in the concept of we know that this thing is convergent. It might help us in the future on whether or not things converge or diverge. So let's go ahead and run through the steps in this. Number one, the first thing I have to prove is that a sub k, that's this term right here, not the k plus 1 with the negative as the base, a sub k equals 1 over k, and I'm going to go ahead and change this to f of x because maybe we just don't feel comfortable taking the derivative in terms of k. Maybe it's easier to take terms in x. So let's just go ahead and change it over to x like we would do in the integral test. And then let's go ahead and change this to x to the -1 because the derivative is a lot easier to take when the power is actually there. So I'm going to go ahead and have x to the -2 times -1, which is really -1 over x squared. And again, it's so important that you logically work through the understanding of these values. This value being positive, and on top this value always being negative, negative over positive, will always imply that we have a negative number. And again, that means that the first step of the alternating series test is satisfied. So I can conclude then that a sub k is always non-increasing. So that's, again, the first statement we need to make about the alternating series that we're working with, and we do have that being conclusive. Now, hopefully in this vein, you've already understood that this thing is probably going to end up being convergent, and the reason why we can make that conclusion is because this thing is definitely going to work. And number two, then, should also work. If for any reason this one or the second statement fails, the alternating series will not converge. So this is one of those situations where you can make a conclusion about the alternating series. This thing is not actually inconclusive. It's not inconclusive actually because of the second statement in most cases. So the first statement could have some faltering pieces, and the second statement can have some faltering pieces. But overall, if either one of these details fail, you may conclude that the series that you're looking at is actually going to be divergent. This one because it's going to increase without bound, and this one because, well, this is nothing more than the limit as k goes to infinity of 1 over k, and it concludes that it's equal to 0 in this case. In other cases, if this thing fails, we're going to get something equal to a number or infinity. And this right here is a step, the only step in the div test. So if we can conclude that this thing is going to be increasing without bound or simply bouncing back and forth uncontrollably, then we can argue that by the div test, this thing isn't necessarily going to converge. So again, the alternating series must have both this detail where it's always on increasing and this detail where it's always equal to 0 for us to conclude then that the series, the sum of -1 to the power of k plus 1 over k, which is the alternating harmonic series, is convergent. And that's it. Again, you're just checking off two specific qualities. There's nothing else you have to do after that. You just have to make sure that the thing is, the terms without the negative values are always non-increasing, and that the limit as k goes to infinity is equal to 0. And then you can conclude convergency. Otherwise, you conclude divergency.